is Nicolas Porto Campana. I'll be the speaker for this presentation. I'm an undergraduate student at Federal University of Brazil. In 2019-2020, I made an exchange program in Università di Modena Reggio Emilia in Italy, where I developed this project inside a company in an internship. So today I will try to present the results and all the achievements of this project. This project is called an integrated task and personnel scheduling problem to optimize distributed services in hospitals. So this is our little agenda. I will briefly describe it. I will make an introduction about where this problem came from and some little infos about the company. Our approach, okay, so I will do a kind of informal description and then a mathematical view of each step. And in the end, I made show you the computational results, okay. So first, the company called Scope Service is a big Italian company that provides a lot of services such as logistics, cleaning, surveillance, security, energy, and facility management. Okay, so inside this company, they have a lot of optimization problems that can be solved. Okay, as this one that will be presented today. Just to see the size of this company in Italy, it got almost 1 billion euros of revenues in 2020, and this figure shows the presence of Scope Service in Italy. So the question arises because Scope Service has almost 50%, half of its revenue is generated by the cleaning and soft services. And in this cleaning software service, one of the strongest lines of work of services provided are cleaning hospitals. Okay, the company is labor intensive. What it means that the company need to manage a lot of employees. So it means that if optimizing the labor cost can significantly brings a cost reduction. So how to organize and plan hospital cleaning as fast and efficient as possible? Why is this problem interesting? So the first point is organizing the cleaning schedules is one of the key points in the operational process inside the hospital. We can ensure a sanitary and cleaning levels. It can also help quickly evaluate and change schedules under emergencies. For example, if you have a department or a report that need to be isolated, for example, and you need to quickly change the schedules, our proposal can help quickly evaluate and change these schedules. And as already said, COVID-19 bring us new challenges about scheduling organization problems. So the scope of this work, we want to model and propose a mathematical and heuristic method to solve this complex hospital organization problem. This problem we addressed as an integrated task and personal scheduling problem, ITPSP, and in the end generate an usable output for the company. So I will make an informal problem description because here, as already presented, our challenge is we have a hospital, and we need to clean the whole hospital with the demands provided by the company, the hospital. Okay, so we need to clean it all. And we'll show how we do this. It's not an easy task. So first we have an hospital divided into buildings. Okay, for each building we have various locations. Okay, in different floors. These locations can be seen as rooms. For example, have a bathroom, have an elevator, ambulance, hall, and every room inside the hospital. Each of these locations can have different categories and attributes such as risk level, size, time windows to clean, etc. Also, cleaning frequency is given for each location. So here we have an example of an input for this part of the problem. We have an ID, the floor where it's located, because it will be important in the next steps. The type, the risk level of this location, the size, and the frequency is worth to say that the frequency here is a weekly frequency. Why? Because company wants to create a kind of a standard week of work. Okay, so when they say 7, say that location 4 need to be cleaned 7 times in a week. Okay, and you need to organize this. The second part, we also have a set of heterogeneous employees with the contractual information, given a planning horizon, for example, 1 month or 1 year, I don't know. The objective is we need to organize all the cleaning routes, okay, all the cleaning schedules, and assign these workers available to optimize these cleaning routes with the minimal labor cost. The objective here is to minimize the labor cost. Okay. So our proposal is a 3-step approach. Okay, we try to kind of decompose the problem into 3 steps. Okay, the first step, we want to optimally make an allocation of all locations into the days, into a week. Okay, based on the demand, the weekly demand. Then we get this output of these first step, put in the second step, and say, okay, for each day, create the set of cleaning routes, the sequence of visit they are visiting for all the days. Okay, and in the end, we'll get the output of step 2 and put it as an input for the step 3, which is the personal scheduling, minimize the total labor cost. Our real objective function that will be seen now later on, it's related to the step 3. This is important to say. So our objective function of the ITPSP aims to optimize the first equation while meeting the operational constraints defined into steps 1, 2, and 3. Okay. So the first equation is roughly the multiplication of a z, small z, and the h, which is the total labor cost. But the small z boils down to the equation number 2. It's only the total working time for all the employees. So in the end, we want to minimize the total labor cost, okay, of the problem. So the first step, okay, we need to we'll do an optimal allocation of the cleaning tasks to days, okay. So our input data is, we have the set of locations, we have the set of visit patterns, okay. For example, here we have 1, 3, and 5. So 1 means Monday and so on, until 7, which is Sunday. And we have these feasible patterns defined by the company, okay, for each location. We have as input data also the cleaning tasks for each location, the respective size and cleaning duration measured in minutes. We have also a beta constant factor. This beta constant factor was requested by the company because the company wants to kind of balance or unbalance some days. For example, in the weekends. The company wants less work, for example. In a summary, what we do, we receive as input all the days, the set of days. There are 7, okay, 7. Why? Because we need to create a standard week of work because company wants to repeat the standard week in the planning horizon, okay, because they don't want to change the fixed schedules and the fixed tasks, okay. It can help to train better the employees and etc. So for each location V, we receive also its tasks and the feasible pattern for this location. And what we do for each day, we define the set of locations that need to be cleaned in that day. We can see that N1, N2, 3, until 7, it means that 1 to 7, the days of the week, okay? So we have N7, for example, the set of all the locations that need to be cleaned at Sunday. How do we do this? We use a mathematical model, a MILP, that aims to minimize the maximum number of daily working hours, okay? So we want to kind of balance into all the days, more or less the same work, okay? The thing I won't describe it briefly here, this model, but just to say that this delta here, inside this delta, there's a pre-processing or a simple calculation that takes in consideration the beta previously presented, okay? So we have as output of step 1, thus for each day, the set of locations that need to be cleaned, okay? So we get these sets and put as input for the step 2. The step 2, we need to create a cleaning routes, minimizing travel distance. It means that for each day, I create a set of cleaning routes, a set of sequence of visits in the locations to clean it. Okay. So as input data, we have the graph, okay, for each building, and its associated traveling distance and time. Also, a time windows for each location and for each task, and a maximum route duration. Okay, this input data we have as input, as I already said, for each day the set of locations that need to be cleaned, and we will generate for each day a set of cleaning routes. Okay, so for the same thing for the first step, we have T1, T2, T3, and T7. It means that, for example, T7, the set of cleaning routes that can be one, can be multiple, cleaning sequence departing from the start point defined by the company and going through all the hospital and turning to the starting point, minimizing the total travel distance. Okay. How do you do this? We use the unadapted randomized variable neighborhood descent. As inter-route movements, we use a cross-exchange, relocate, and swap. And intra-route movement, we have a to-opt and swap. All these movements are well known in the VRP and TSP literature. We use it also a first improvement policy. And the different thing here, we use it local movements. Okay, local movements here means that we want to exclude far enough locations. It means that we only evaluate and we only try all these movements with the locations that have L-1, L, and L+1 to create a kind of an interval that we need to. And also with this local movement, we apply only a few % of the local movements because as we have, will be seen, as we have a big hospital, also with these local movements, okay, evaluated with only L-1, L, and L+1, we have yet a lot of possible movements, okay? So we apply only a few % of these local movements. And we do this with eta iterations in this algorithm. So we came from the second step to the third step. So we have now for each day in the week, we have a set of cleaning routes, okay? And then we need to get these cleaning routes, and we need to get the available employees and assign to these cleaning routes, okay? So we receive as input the output from the second step. So our input data is the set of employees with its contractual type. For us here, determining the maximum number of days that each employee can work because it's contractual. The maximum amount of days, okay, that any employee can work consecutively without a rest day, and the maximum amount of working hours per week, defined the ME. The number of days associated to the scheduling period, it here for us would be the planning horizon, okay, delta, and in the end, the labor cost H. So in summary, we receive as input for each day the set of cleaning routes, okay, and what would we do? We first pack these cleaning routes into daily duties. Okay, we call daily duties. It means that we get one or more cleaning routes that don't overlap, surely, because we can have only one employee working in the same time. Okay, so we pack one or more cleaning routes to one day, okay, and try to assign the employees into these daily duties. Okay, so this is the idea for the third step, and always minimizing, surely, minimizing the labor cost. So our heuristic algorithm here, it's very simple. We first create these daily duties using the best fit approach, because we want to have the compact daily duty as possible. Okay, we try to avoid the waiting time between two cleaning routes. We then assign the employees to the duties, okay, minimizing the labor cost. And in the end, we try to do a simple local search that here we just try to swap a whole week in between two different employees, or we try to swap 2 days in 2 different employees. There are both the procedures that we implemented. Okay, but running this proposed algorithm only once would generate a locally optimal solution, okay? This is caused because our myopic view of one step to another. For example, that can be seen here. The first objective function don't know the second objective function that is minimizing travel distance, and the third objective function that is minimizing labor costs don't take in consideration the previously optimized objective functions, okay? So you have a kind of myopic view. So for each step, we lose a little bit of, how can I say, optimality if we are trying to solve, for example, this whole problem in one shot, for example. So what do we do? How to address this problem, okay? So because we have a kind of a different objective function for each step, we used a Hamming constraint, okay? So the Hamming constraint, we add this equation 8 to the first step model, okay, that previously presented. It can be seen here, this mathematical model, okay? We add here this constraint and explaining it. For each iteration, the algorithm keeps the variable VP, okay? That means that location V chose the pattern P, okay? And in the next iterations, the constraint 8 says that a number C of variables must be different from the previous iterations, okay? These modifications allows the algorithm to possibly arrive in other local optima, okay? We will be seeing what happened to the objective function if we apply this iterative approach, okay? Here we have an instance that we created, an artificial instance to show the behavior. If we run only once this algorithm, the proposed algorithm, we get this objective function. It's also on local optima. But what happens if we keep iterating? So we can possibly arrive in other local optimas. We can also get worse values from the first iteration, the first running, okay? But possibly in the later iterations, for example, in iteration 21, we get a better result than the first running, okay? So this is more or less the behavior of this iterative idea of changing the variables on the first model, okay? So for our computational experiments, the thing that's it's good to say here is we use the CBC solver, okay, of CoinOR, the project CoinOR in our Nuke model, okay, and all the other configurations. For all the experiments, we used the following parameters, values always defined by the company, okay? We used a balance factor. Here, the balance factor, just remembering, are how much the company wants to balance or unbalance, in this case, some day, for example, in the weekend. So the company wants half of the work in the weekends, okay? We have also the maximum route duration because we want the maximum route of 8 hours, okay? This is a law in Italy, so we use this value. We also used a maximum waiting time between two cleaning routes, okay, of 20 minutes. The maximum consecutive working days of 6 days, it's also Italy law, okay? So you need, after 6 days of work, the employee need a rest day. We use also a planning horizon of 14 days. And these both values, the total CPU time and the amount of evaluated movements in the second step, 10%, are set after some experiments, okay, these both values. And we also have the value, the velocity of 15.6 meters per minute. This velocity is the velocity of going through the edges of the graph, so going through one location to another inside the building in the second step, okay? And how did we get this value of 15.6 meters per minute? We created a discrete event simulation model to try to find the best employee velocity, okay? So we used the algorithm output, the cleaning schedule of the second step as an input for the simulation. We add some disturbing agents. We calculate using a confidence interval, okay? And the result obtained was me equal 15.6 meters per minute, sorry. So here we have some figures of the hospital recreated in any logic software, also with the elevators and the time between going from one floor and everything. So it was a very good simulation. So for our instances, how did the real instance was obtained? We created with using BIM, a building information modeling, which is a data model that stores different types of information and consists of parametric objects representing building components. The original building contains 15 floors with a total of 2,422 locations, not uniformly distributed and divided into 47 types. So it's a very, very, very big hospital, okay? And just to imagine, for each day, if each location have only one demand for clean in one day, we have for each day more or less 2,000 points to visit for. So we are solving a very big problem. Here we have the 2D vision for the instance. So it's the kind of a 2D plan of the hospital. Here you can see all the locations that we are saying, okay? So we have the identifications inside. You can see the locations, all the elevators, all the hall, the bathrooms inside and everything. So, and here we have the 3D vision of the real instance, okay? Just to imagine how big is this hospital. So the results for the real instance. The tests were performed using the combinations of eta, that means the number of iterations for the algorithm in the second step, okay, the adaptive variable neighborhood descent, and XC, that is the number of variables that need to be changed in the first model of the first step, okay? So these were the parameters that we use, and we created the combinations, the product for these both sets, and try to define the best for the real instance. So the percentage shown in the table is calculated with this equation here. The ZC means the objective function given by the company. Okay, so this is the value that the company has. And we were able to, with the combination 40 and 1, okay, achieve a 5.83% of gain. It seems not so much, but if we replicate, because we use it for 2 weeks, if you replicate this for a whole year, we can save a lot of money, okay? So we also generate an artificial instance. We generated 20 to be exact, more precisely. And how did we do this? We get the real instance, selected randomly subset of floors, okay? Then we kept the information, the original information, okay, of these floors, also each location for each demand and everything. And then we create a new instance by sorting the selected floors in arbitrary fashion. Okay, this we created in this way. And for all this instance, sorry, we have tested all the combinations previously presented for the real instance, and in order to find the best combination to run the algorithm. And the table shows the summary of the results. Okay, for all the artificial instance created. And the best combination found was eta equal 20 and xi equal 50, based on the most occurrences. Okay, so we get running for all the instances and see if which combination get the best results and appears the most. So which is the result for the company? Okay, the output for the company. First is a Gantt chart where you can see for all the planning horizon. Okay, here I have only 2 days, but it's just to illustrate. So you have a Gantt chart to show the planning horizon, all the scheduling for each worker. For example, here for each row is a worker. Okay, here we have the midnight where the days end and the 6 a.m. where the days start. Okay, and each bar is a route. Okay, so you can have here you have two routes that was put together. Also here we can see by the different colors. Okay, and other output. This is the how can I say the very usable the very useful thing for the company is a detailed Excel file showing for each worker for each day the sequence of visiting for each worker. Okay, for each employee. Sorry, for each employee. So, for example, employee 3 in Monday need to visit the location 1, 5, 6, and 9 and turn back to the starting point. Okay. So the conclusion: the proposed algorithm was capable of generating good solutions with acceptable CPU time. Okay, and it's I can say that company usually do all this work by hand, so it takes more or less 1 month to complete all these tasks. Okay, so we were able to achieve how can I say a good result with half an hour, and if you want you can put the algorithm to run longer times, 1, 2, 3, 1 day, I don't know. And the algorithm was able to improve 5.83% of the current company solution. As I already said, the Coop service spends a considerable portion of its budget. It's a labor intensive on labor. Okay, so more than 2,000 employees. So it's crucial to have an artifice to properly administrate the personnel and the tasks, particularly during emergency circumstances such as epidemic crisis. So future research may consider first the insertion of a more complex cost function in the first equation that could take account of different employee levels. Okay, for example, seniority, time, experiences, etc. A more profound economic cost analysis related to the labor cost. Okay, assuming it differs across workers and changes over time. Okay, and in the end, incorporate meta-heuristic strategies such as perturbation schemes in steps 2 and 3. 2 is the creation of cleaning routes. Okay, and the third is the personal scheduling. Okay, so incorporate meta-heuristic strategies in both steps. So it is. Thank you for your attention. Feel free to ask me any question, and I put some references here to if someone is interested.